Hello, my name is Edward Vittel, and my group members were Desmond, Chris, and Daniel, and for our group project, we decided to do Rust. So why we chose Rust, we liked the language features that Rust had, like pattern matching and memory safety, and since memory safety is increasingly relevant, we thought, perhaps this is a good thing to understand. So like memory safety, Rust has a number of features that are borrowed from functional languages like SML, like variable immutability, pattern matching, implicit return, underscore wildcard, and more. And it also has similarities to Chapel. There's parameter intents, which we'll touch on, and no dynamic linking, which allows for a very slow compiler similar to Chapel. But in any case, this allowed us to easily implement a language that we specified that is somewhat of a subset of MIPS that has a few additional instructions like print for the ease of testing that allows us to showcase these features. So I will just give a brief tutorial of the language first, Rust. So your first program, Hello World, we can create a new project using Cargo, which is Rust package manager and build framework. So this is what Hello World would look like. As you can notice, println is a macro, which Rust has, but I won't touch on very much, just thought it was something of interest. So cargo build will compile your code, and cargo run will run it. So variables by default in Rust, as I mentioned prior, are immutable, and if you try to change them by default, it will throw an error. Interestingly, you can also make them mutable by using the mut syntax, so you can change them after they're instantiated. And there's also different sizes, which are specified, as you can see here, like I32, U8, F64, and so on. So that's the primary type, like a char would be a U8, so on and so forth. Pretty intuitive. There's also tuples, as you can see here, and here's a comparison to the tuple syntax in Chapel. So, as I mentioned prior, Rust has a number of memory safety features like ownership and borrowing. So as you can see, in this example, we're passing S as a reference, so that allows the callee to borrow it. And borrow checking allows us to specify parameter intents similar to Chapel, and will make sure that the reference is used in an appropriate way, which means that we don't have to manually free, and this makes the language much more safe. So there is manual pointer management, but you will have to use the unsafe keyword, and I won't really get into that since we didn't really want to use that for this project. So pattern matching, this is a basic example, one that's very intuitive and comparable to, as you can see here in C. It's a little bit more compact, but again, here we're using the underscore wildcard instead of the default case. Rust also has structs, as you can see here, pretty intuitive to use, as one might expect, using the dot syntax. And we can have implementations using the impl keyword, and we can have something like a constructor, which allows us to have, somewhat of OOP-like functionality. So structs also have pattern matching, as you can see here, which is pretty cool. One of the biggest powers of Rust, similar to SML records. And there's also enums, which have fields similar to a data type in SML. Here's one example. You can traverse them using the 2: syntax, and you can have something like an optional type. So here's an example, and here's the analogous code in SML.
Hello, my name is Daniel, and I'm going to be talking about some of Rust paradigms and features, as well as comparing it to other programming languages that we've seen so far. First, I want to start with Rust's primary design goal, which is systems programming. Rust is built to give developers low-level control over things like memory performance and direct access to hardware. This makes it ideal for writing things like operating systems, embedded systems, or other applications where you care about resource management. Rust isn't just low-level though; it also brings in functional style influences. Variables are immutable by default using let, and you have to explicitly opt in to mutability with mu. It also supports pattern matching through constructs like match and if let, and offers algebraic data types such as enums that make code more expensive and safe. Next up is generic programming. Rust supports zero-cost polymorphism using traits and type parameters. Alongside that, trait-based polymorphism replaces traditional inheritance. So instead of classical object-oriented hierarchies, you use traits to define shared behavior across types. Next up is concurrency and parallelism. Rust type system helps you write multi-thread code safely by preventing data races at compile time. Now I'm quickly going to talk about some of Rust key features. We have ownership and borrowing, compile time memory safety without garbage collector, and a strict system of ownership and references. We have zero cost abstractions, high level constructs compiled down to minimal runtime cost. We have error handling with option and result. We have macros, both declarative and procedural. We have module and package management, mod/use system with cargo for building, testing, and publishing. We have unsafe code, which are unsafe blocks that allow you to perform low-level operations, and they have to be purely marked and isolated. Then we have FFI interoperability, which allows easy calls to C or C++ code via extern blocks and #reprc. Moving on to Rust versus Chapel, we have design goals. Rust was designed to be safe, low-level systems programming language with zero-cost abstractions and manual control over memory and performance, while Chapel is more productivity-focused, parallel/HPC programming based on a partition global address space model. Then we have memory management. Rust has an ownership and borrowing system checked at compile time with no garbage collector, while Chapel has a garbage collector and supports manual memory control through unmanaged types. Next, we have concurrency and parallelism. Rust has explicit thread tasks with data race freedom, while Chapel has built-in parallel loops like for all, co-for all, with scalable tasking layer and support for distributed memory via locales and domain maps. Next, we have safety guarantees. Rust has memory and thread safety guaranteed at compile time, while Chapel has high-level race-safe constructs, but lower-level shared data can still race if not used carefully. And we have typical use cases: Rust, embedded systems, OS kernels, web, backend, CLI tools, networking services, while Chapel has high-performance scientific simulations, parallel algorithms, and large-scale data processing and distributed programming. Moving on to Rust versus SML, we have paradigms. Rust, multi-paradigm, imperative plus functional influences, while SML is more functional. Memory, ownership, Rust ownership and borrow checker with no garbage collector, while SML has automatic memory management with garbage collection. Type system, Rust allows explicit generics with trait-based ad hoc polymorphism, while SML follows a Hindley-Milner type inference with parametric polymorphism. They both offer algebraic data types and exhaustive match and case for pattern matching. And typical uses like Rust, same as we saw before, system related, and SML language research, teaching functional programming like this class, and rapid functional prototyping. Now is Rust versus C. We have paradigms. Again, Rust, imperative and functional, and then C, imperative and procedural, close to hardware with manual state and control flow. Memory safety, again, Rust, no garbage collector, ownership and borrowing, and then C has malloc and free point and pointer arithmetic, which makes it easier to introduce buffer overflows, leaks, or dangling pointers. Then next we have performance overload. Rust has zero cost abstractions, high level constructs compiled down to minimal overhead, while C has bare metal performance, minimal runtime by design. Then we have typical use cases, like we saw before, Rust systems, but also C is very system-like, operating systems, drivers, embedded firmware, and performance critical libraries. So both of these are used for systems programming, but Rust offers additional safety features that C doesn't. Okay, lastly, I'm going to do a quick summary of Rust versus these other programming languages. As we can see, Rust either fully supports or partially supports most of the things we talked about, except for high-performance computing and scientific computing.
Hi, I'm Chris. This is a very brief history of Rust. So, its genesis, right? Rust first began its development as a personal project by lead designer Graydon Hoare while he was still working on Mozilla. And this project kind of started as a personal way of trying to create a programming language that is fast and efficient. Kind of a metaphor with its name that got chosen, Rust, which is after a sort of fungi that is over engineered for survival, right? So it's trying to be as fast, efficient as possible. Now, this name is a bit of a misnomer because the name was actually chosen because he just thought it sounded cool. Uh, but in its early creation, when it was still kind of a secret project, no one really knew about it inside of Mozilla, he based it off of older languages like Clue, Erlang, and Limbo. So a lot of those older languages really kind of informed Rust's creation very early on. And in these very early days, Rust was actually, its compiler was written in OCaml and had some features that were actually left behind, including object oriented programming and type states. So while this was still being worked on in secret for years on end, right, at some point it kind of had to leak, right? So gathering troops. In 2009, Hoare finally talked about Rust with other people, right? And a small sort of coalition of people came together to work on it to the point that it actually got some support from Mozilla inside that's officially sponsored Rust, right? They wanted it to be kind of a safe web browser engine. They never expected it to take off as it did, right? At this point, the programming team kind of kicked into high gear, and they worked pretty hard on Rust, right? Then, approaching the year 2012, once we got closer to the release, a bunch of development was super experimental with new things being put in, put out. It was crazy. The first public Rust release was released in 2012, and the language was well received enough to kind of continue getting support from Mozilla. And no one really kind of expected what would come with Rust. Once it was out there and more changes took place, a bunch of new forming and new work was put in for Rust that made it faster and more efficient to the point that it got this big following. It got rid of type state and any pure functions. It streamlined its language features, removed garbage collection, instead just having a refined ownership system, which became the standard for Rust memory to the point that people were like that. Around 2013, actually, Graydon Hoare, the creator we were talking about, actually stepped down as leader, and instead a federated governance of developers kind of came in to kind of guide the destiny of Rust. Its official stable release came out in 2015. Rust is history. Rust continues to evolve to this day. And I gotta say, how is Rust even used today, right? Like, since I'm saying it's been evolving and all that. Why and where is Rust used? Rust is actually used in a whole lot of applications, ranging from the expected to kind of the unexpected. Especially the web dev and systems. It has very cool tools, especially in web development, using ActX Web Framework and all that. And then in systems programming, in kernel modules, firmware, all that great stuff. In networks too, has a lot of really great networking software libraries that make it really fast and efficient, including Tokyo Software Library. I'm going to shout that out. Even game dev and data science, which was kind of a strange one I didn't really expect. In game development, Rust actually has some engines that are very similar to C++, making the switch not too bad. A lot of documentation with Rust game development. And also data science. Rust is very fast, very efficient, very good at performing critically fast and safe data analytics. In conclusion, Rust has really become a popular and prevalent programming languages. One of them, because of all the really interesting tools and features that it has, even becoming one of the most admired programming languages, from Stack Overflow. It's been nominated as the best for 4 years straight, and 12.6% of developers have said that they've been using it a lot lately. And I think Rust is really, truly here to stay because of that, the history and all its uses. Thank you.
All right, I'm Desmond. I'm doing the code walkthrough. So we made a virtual machine that can basically just execute assembly instructions. So here we just have a list of all the supported instructions and what registers we have. So we have a frame pointer, a stack pointer, a return address, the constant 0 register, and we also have 16 general purpose registers, R0 through R15. So as an example instruction we have like add immediate, so it basically takes in a destination register, and then a register value to add plus an immediate value. And then we also have instructions that like operate on 2 registers and stored in a destination register. Then we have stuff like arithmetic negation that just operates on 1 register. We have multiply and divide that put their result in the special high and low registers. And then we have move from high and move from low to access those values. We also have load and store for accessing stack memory. We have just a print instruction that will just print out what's in a register. We have some branching, so we have branch equal to, we have branch not equal to. We also have like jumping, so we have a jump instruction, jump and link, jump register, and then we also have halt, which will just stop the program. And then we, of course, have labels. So basically how we're modeling everything is with Rust enums. So like for the register, for example, it's an enum where it can take on 0, frame pointer, stack pointer, return address, high, low. And then a general purpose register, where here it's basically just simple R, but it's also wrapping an 8-bit unsigned integer. And then instruction is similar, and then it's an enum that's just has all the different types of instructions. And then each one of the instructions is sort of like a struct. They also held values, so like you hold the registers and the label for branch equal to and that sort of thing. And then we have basically a program that is just made up of a vector of instructions, and a vector in Rust is like an array list. And then it also has a map that basically maps a label to its offset into the program. And then we have some traits implemented in the program for getting instructions, getting an offset of a label, getting the length of the program, that sort of thing. And then this is the main entry point into the program. So basically what it is going to do is it's going to read the command line arguments, and it's going to parse out a path to a file, which is what's going to be executed. And then once it parses out that path, it's basically just going to pass that to the scanner, which is going to open up the file, and then it's just going to go line by line and parse out if it's an instruction or if it's a label or if it's just a comment or white space or whatever. So basically for parsing out an instruction, it's just a gigantic match statement, right? And it'll just match on the first token to figure out what instruction it is, and then parse register is similar. It just matches on what token represents the register. And then it'll also parse out labels. And then once it has a program, it's going to pass it into execute. And basically what execute is going to do is it's going to enter an infinite loop, and then it's just going to get the next instruction and execute it. And it basically keeps track of everything with a context that basically stores what the program counter is, the register pool, and then the stack. So the register pool is basically just the value of all the registers, and it has a few traits implemented, like creating a new one. You can set and get a register from it also. And then basically for each instruction, it's just going to do a match on it and figure out basically what function to call. And then the functions will usually like take in the immutable borrow of the context, as well as like a destination register, that sort of thing. And then you can look at some of these. So like add, basically it's going to take v1 and v2 by just getting the values out of these registers, and then it's going to add them together, and then it's going to call set register to store it back. Yeah, and then to test everything, we have this shell script here where it's basically going to go through every program in our sample program directory, and then it just has an expected output and an output, and it's basically just going to run diff on that. So if I just run that real quick, it'll tell me that we're good to go here. So